Welcome to the first video for Lecture 4. Lecture 4 topics are about Introduction to Dynamic Process Control. Most of you have very limited experiences with process control, and these slides are designed for those who don't have any experience. So some of you might gain a lot of information from this lecture, and for those who does have some experiences, you might find it to be a review or a different way to look at this topic. Okay, start over. Welcome to the first video for Lecture 4. The Lecture 4 topics are about Introduction to Dynamic Process Control. Most of you have very limited experiences with process control, and these slides are designed for those who do not have any experience. So some of you might gain a lot of information from this lecture. And for those who does have some experiences, you might find it to be a review or a different way to look at this topic. We will begin with the definition of a process and discuss the types of problem solving covered in this course. Problems found in this course is the simplified version of problems you will see and solve in industry after you graduate. In Section 1, we will give an overview and introduce several related terms. And in Section 2, we will give a simple differential equation as an example that will be solved analytically. There are many definitions about process. Here we quote Spedding's definition of process, which is a series of controlled actions, changes, or functions that bring about an output or product over time depending on inputs and external factors. For process control, actions and changes are controlled to produce an output that meets some specified criteria. Some points about process control we will highlight here are there are one or multiple inputs. There are processes that involve a series of changes and outputs. In most cases, the order and time are both important for completing each step of change. There is an output which has the desired characteristics. All of the characteristics are part of the dynamic process, which we are going to control automatically. And some simple dynamic process problems that we are going to solve in this course include fluid heating, liquid level and flow, mixing without reaction, and bioreactor with reaction. We will not include problem solving for electrical circuits or motion and position control. The goal of dynamic process control is to adjust inputs to maintain process output within acceptable tolerances. Inputs and disturbances might change with time, and process control must deal with these input changes. For a fluid heater, which can be a water heater, the water flow rate and the inlet temperature might change with time. The ambient temperature could also be a factor that affects the output. External disturbances are uncontrolled. For process control, we need to adapt a dynamic analysis to assess the process response. The process response will depend on the process, the sensor, feedback elements, control mode used, and the actuator used. We will talk about process response later in the course, but it is one of the reasons for all of the mathematics and approaches happening at the beginning of the course. Many engineering problems can be analyzed using steady-state analysis. Steady-state analysis can be used to decide many of the components, but to see how the whole system reacts to dynamic changes, you need to conduct a dynamic analysis. When we have time-dependent problems, we end up using ordinary differential equations. Do you remember them from previous courses? Many useful results can be found using simplified ODEs. We also make several assumptions to keep the analysis manageable. It is important to keep track of the assumptions. Again, the dynamic processes are described by differential equations. The abilities to solve or approximate the solutions of differential equations have grown tremendously in the past 10 to 15 years. there are many powerful tools to analyze process control dynamics. Modern control system uses state space concepts and matrix vector analysis. We will not use these methods in this course. However, we will focus on analytical and Laplace transform solutions for solving differential equations instead. We will use MATLAB to solve differential equations or put them into a useful form for us, and to plot model results. You will see this diagram many times in this course. It is called a block diagram. It is a simple diagram that plots the generic elements of closed-loop process. By the end of the semester, you should know each element and analyze each step. Process converts inputs to the desired output. By the definition of process, which is a series of controlled actions, changes, or functions that bring about an output or product over time depending on inputs and external factors. A process has one or more inputs that are manipulated or controlled, and external disturbances include uncontrolled inputs or factors that affect the process output. In this course, we will deal with one controlled input and a single measured output. A closed-loop process has a sensor to measure the process output. Depending on the process, the sensor might measure temperature, tank level, flow rate, pressure, color, brightness, or some other relevant physical property. We will usually indicate the existence of a sensor at the output with a circle. The sensor output is the condition for the feedback element. The feedback element converts the sensor output into a useful input for the comparator. Here, the raw sensor output usually needs some conditioning to make it useful. On the left-hand side of the figure, we have the set point, which is on the left of the comparator. The set point is used to tell the controller what the output is desired. A manager or operator decides the desired output. For example, the temperature setting in a thermostat is to tell the furnace or conditioner to turn on and off. A cruise control in a car sets the desired speed as the set point. This set point is set by the driver and sent to the controller for cruising at a certain speed. A comparator calculates the error between the set point and the feedback. Ideally, if a process is well controlled, this error will be small. But if input changes or external factor changes, the output will not match the set point. Controller uses the error value to determine control signal and send it to the actuator. There are different types of control or control modes that can be used. Some controllers are simple on and off controller, such as the thermostat. Some controllers are proportional, integral, and derivative control in some combination to convert the error into a control signal to adjust to the actuator. Finally, we have the actuator. This is the element that converts the control signal into an action that manipulates the input. Example actuators include relays, solenoids, solenoid valves, and motors. So this simple block diagram with each of the main elements will be covered across the semester with problem solving for fluid heating, liquid level and flow, mixing tanks, bioreactors, etc. Here is a list of example processes that are automatically controlled using closed-loop systems. The concepts will be easier if you can relate physical meanings to them. This is the end of Lecture 4, Section 1. Please write down any questions you might have and bring them to class to discuss. Thank you.